So can I start now?
Okay. No. We just started now.
Uh-huh.
So I'd like to welcome everybody to
Yeah.
today's
Mm-hmm.
session of
Mm-hmm.
the CNPS. Um, I'll bring. Sorry, I need to bring everybody else down except myself just to introduce the show today. So you're all very welcome, whether you're entering through StreamYard, through the social media links, or whether you're in the green room. Uh, my name is Ian Cowan from Dublin, Ireland, and I'm hosting these fortnightly technical sessions. And I had to be a little careful yesterday on St. Patrick's Day to make sure that I would be capable of hosting today's meeting. So I had to be a bit laid back. But now, today we have an interesting speaker, Mr. Henri Corniere. I hope I'm pronouncing the name correctly, from Vancouver, British Columbia, in Canada. And he's very kindly started very early in the morning. There has been a time change actually in North America, but not in Europe. So we don't change for another week or two. We in accordance with custom, we tend to stick to U.S. Eastern Standard Time of 10 a.m. So notwithstanding the change in clock, we're still starting at 10 a.m. Eastern Standard Time in the USA. Now, Henri published a paper called "The Great Power of Prediction from a Massive Photon Hypothesis" in the Journal of Advances in Physics, Volume 20, 2022, last year. And this was drawn to our attention. So we had the temerity to approach Henri. I think it was Dennis Allen, who really took the measure there to go ahead. And we've been in correspondence with him for some time. And he's very kindly agreed to give the talk today with the title Mass Photon Theory. So a non-zero mass photon. The brief description would be: a single ponderable tiny photon frees the mind of old ways of thinking and opens up new paths to a broad field of investigation where the very large can be described and explained by the very small. So I take it as a sort of an integration of the very large and very small, which are conventionally quite separately dealt with in mainstream physics. So maybe there'll be some integration there. And I've had a look at the paper, but I'm looking forward to Henri's bringing us through. Now, there'll be something like 50 minutes to 1 hour devoted to uninterrupted presentation. And Henri has a number of slides, which unfortunately we haven't been able to get him to project. So rather than waste any more time, I have them here on my computer, and we'll project them when he tells me to. There are about 6 slides, and he'll go through them. Now, I think if there's something really urgent, he said something that you don't understand, or maybe ask me to repeat it, you could interrupt. But we'd ask you to keep your questions and answers until the very end of the session, after the first hour. And then there'll be an opportunity to pose questions either on the chat, if you're through social media, or in the green room. I will bring you up and you can actually speak face to face with Henri, and I can chip in as necessary. So I think that's all I need to say in introduction. And I'll now hand over to Henri. I'll add him to the stream, and I'm going to remove myself. And so you will forgive me. Henri will tell me when to bring up the slide 2, 3, 4, 5, 6, 7, and there may be a little delay in my doing that, but I'll respond to his prompt. So without further ado, Henri, the floor is yours.
Okay. Hello, everyone. First, I give a few words about myself and how I came up with this photon mass theory. I was born and grew up in a western city in France called Nantes. I did scientific studies there at the university and got a master's degree in science, but at that time I wasn't satisfied at all by what had been taught to me in physics, like relativity theory or the photon particle without any mass. So I decided not to pursue my studies and in the academy and switch to a professional career as a field electronics engineer. Then comes the time for retirement age, and that gave me plenty of latitude to think and investigate about some topics in physics. When I learned about the massless photon as a consequence of relativity theory, I said to myself that there should be very serious mistakes in physics. How can it be? This is like putting the cart before the horse. There are no theories in physics that make laws for the universe. Nature doesn't care about our theories. Instead, laws, laws in the universe make or unmake our theories. Theories must fit the data, not the other way around. So we must connect the past mistakes. We must correct the past mistake before going further. Otherwise, scientists will make only marginal progress in physics, as it has been the case for, say, the last 5 decades or so. So let's correct the mistakes first, starting with the photon mass. We can make a photon mass hypothesis considering that all other particles carry some mass, except maybe the hypothetical gluon, and even we are not sure about it. The neutrino particle also was supposed to have no mass, but after the discovery of what has been called neutrino oscillations in the 90s, this has been ruled out. So, should the photon particle be massless? We can now start with the photon mass concept. By definition, identical particles in a volume form a gas. There is a photon gas filling all space, and so with all these things considered, this is not a weird idea after all. What is bizarre instead is the absence of mass for particles, and in my opinion, mass and matter cannot be separated as it is done nowadays. The idea that the whole kinetic theory of gases developed for atoms and molecules in the 19th century could also be applied to photons, but as you know, the size is quite different. It's about 1,000,000 times smaller for photons. So we have to jump from nanometers for atoms and molecules to femtometer size for photons. So question is, does the kinetic theory still work at that very small scale? Let's find out. Let's try it, but before, we must say a few words about the cosmic microwave background radiation. This this cosmic microwave background radiation, CMB for short, has been discovered in the 60s. The CMB has been found to have a thermal radiation spectrum in the microwave range of wavelengths. It, follow, it follows very closely the Planck's blackbody spectrum, and it is said that it is the most precisely measured spectrum in nature. It is a perfectly black body. It is also isotropic with a faint and very smooth thermal glow with temperature variation of no more than 1 part in 100,000, which is insignificant. These are very weak radiation can be considered as irrelevant. Still viewed as a fossil radiation that happened some 800,000 years after the Big Bang, during the time of what has been called the recombination period. Finally, it is considered as a landmark evidence for the Big Bang theory. There are two main features which has been measured by satellites. There is a peak frequency of intensity of the spectrum around 160 gigahertz with a wavelength in the microwave region. I deal with that feature later on. And there is an also important feature is the temperature. Determine it to be 2.7 Kelvin by observation with balloons and dedicated satellite in the 90s, like a Kobe satellite or Planck satellite. And he had been refined to 2.72548 Kelvin by comparison with the blackbody radiation curve. Excuse me. So this is a very precise, accurate measurement with five decimal places. This has been this has been done with a comparison of the blackbody radiation curve, the Planck. That temperature of space measured in our galaxy neighborhood and not elsewhere is the sole parameter on which this theory has been developed. Okay, slide number 2, please. Good.
Sorry, just quickly there, Henri. I think the participants will have to maximize their screens to make that legible.
Yeah.
So I'm going to do that, but I think you're going to have to maximize your screen. Otherwise, it'll be a bit small. Okay.
We can read it.
Excellent.
Yeah. So photon gas. Let's talk about the photon gas now. Is it an ideal gas? Should have or should be perfectly elastic collisions. The photons are elementary particles. They are not created nor destroyed. That means they are stable and they are in random motion in space. There is no charge. There is absence of interactions between photon particles. There is also, because the gas is at very low pressure, there is also a very large interparticle distance. These are all the requirements necessary to have a photon gas treated as an ideal gas. And we will see that it is important. So is there any trouble to apply the kinetic theory of gas? There is one difficulty, is to know the number of degrees of freedom for the photon particle. We must know that first because we have to apply what has been called the theorem of equipartition of energy. It gives the mean kinetic energy according to the number of degrees of freedom, where the internal kinetic energy is equally shared between all the accessible modes of motion. This is the definition of this theorem. So we have to know what are the different modes of motion. QED, the theory of quantum electrodynamics, tells us that the photon is traveling in a straight line to the left or to the right, so to speak, leading to 2 degrees of freedom. However, experiments with electromagnetic waves tend to show that the photon path inside a light ray is much more complex. The microwave waveguides show that photons follow each other with a helical trajectory, like a helical spring. This implies that we should have many more degrees of freedom, and 6 degrees could be the right number. It should be an even number. Because if it were not, we won't have a quantum of photon energy. It will be it won't be a whole number. So it must be a whole number for sure. This is the quantum. So we can try with 6 degrees of freedom. Let's try. So we put 3 degrees of freedom for translational motion, X, Y, and Z. 1 degree of freedom for the intrinsic angular momentum, and 2 more degrees of freedom for left and right polarization, which is called helicities. So that makes so each degree of freedom has 1/2 of kT. K is the Boltzmann constant, and T is the temperature of contributing energy. So this gives a quantum of photon energy of 3 kT. That's the minimal amount of a photon amount of energy a photon can possess. This equals to mc squared. So we can write down mc squared equals 3 kt. I put index zeros here, m zeros for the photon mass, c zero squared for the light squared, the speed of light squared, and k is the Boltzmann constant. So this is the tangible derived equation that must be confirmed regarding the number of degrees of freedom before going further. So please, I need the number 3 line. P, yeah, number, voilà. Here I have made I have written a diagram showing that we can calculate the pressure of radiation in two different ways. This all starts with the CMB energy density expressed by the Stefan-Boltzmann law, which describes the power of P related to a black body per unit area. So CMB energy is expressed by capital U, that's the energy, equals sigma T at the power 4, with T equals 2.72548 Kelvin, and E is a constant, we get the energy density of the CMB to be 4.17 10 minus 14 Pascal. That could be expressed in another unit, which is the joule per cubic meter. That's the same that's the same unit instead of Pascal. But it is a pressure, so we can put that in Pascals. I put the word entity there because we don't know yet what is making the radiation, the CMB radiation. But something we know is that it is a black body. So we can make a theoretical model with a cubical cavity, and it has been found that the radiation pressure is just 1/3 of the CMB energy density. So we can calculate it and we get P, the pressure is 139.156 10 minus 14 pascals. That's the first part to the right. And to the left, we can ask a question, is the ideal gas is it an ideal gas, actually? If it is an ideal gas, we can apply the ideal gas law, PV equal NKT. And we can transform this expression by multiplying and dividing at the same time with a factor which is 1/3 of the mass of the photon, 1/3 m0. So we divide it and we multiply, and we can transform this expression this equation by another one, which is pressure equal 1/3 of rho C0 square. Rho is the mass density or the mass of space. And I put the details here in the middle of the box, and we can calculate successively the energy of a single photon in joule, and also the number of photons per volume. It turns out that we have around 370 photons per cubic centimeter zipping in that little space. So we have now the pressure, which can be calculated again, and it turns out that it is exactly the same pressure that has been found with the first pass on the right. Exactly the same pressure. That means that the ideal gas law, which has been written on the left, validates the first equation. Photon gas is a black body and an ideal gas at the same time as well. That means the calculations which we are doing right now are not approximate, they are accurate. They will be approximate if it were not an ideal gas, but it is not the case. It is accurate. We can note that space is weighty. It has some mass, a very small mass indeed. It is in the order of 10 minus 31 kilogram per cubic meter. As a bonus, we got another equation in the form of C0 equal square root of 3p over rho. And what has been confirmed here is that only 6 degrees of freedom, or the quantum of energy 3 kT, as theorized, fulfill that equation. We can try 2, 4, 6, 8. I repeat, we must have an even number, and we won't get that equality. So it is confirmed that we have 6 degrees of freedom instead of 2 for the photon, and that the gas is ideal. Okay, let's go to the slide 4, please. So this is a tangible, the last equation is not the last, but the first one is a tangible equation, the derived equation that must be confirmed before going further. So here I put two equations, and you can already see that those two equations are exactly the same ones for the speed of sound. We can calculate right now the mass of the photon by m0 equals 3 kt over c0 square, and we get the mass of the photon to be 125,604 10 minus 39 kilo. It is a very small mass, but it is not a zero mass. So it has been confirmed here that the mass of the photon is not zero. Let's see, let's take a look at the second equation. For the sound waves, it is written as C, like accelerators, equal square root of gamma, the adiabatic index, instead of 3, P over rho. The speed of sound depends also of the kind of atom so you see the two equations, they are the same, and this is the important point, that for the sound wave, the speed of sound, the adiabatic index has been replaced by factor 3 for light. Now, can the speed of light be predicted with the two equations? Answer is no, because we need the speed of light in the first place to determine the mass m0. So it is not possible to do that right now, but we see that further we see that in a moment that it is possible to predict the speed of light and also the Planck constant directly from the CMB radiation. We'll see that in a moment. Another interesting fact is looking at the first equation. We can see that the speed of light depends on the temperature, the absolute temperature of the gas, on the square root of the absolute temperature of the gas, I would say. This is important because we are sure that there are hot spots and cold spots throughout the universe. So the speed of light cannot be the same everywhere. And I take two examples here to illustrate that fact. There is a nebula called the Boomerang Nebula in the galaxy, some 5,000 light years away, and the temperature has been measured to be just 1 Kelvin above absolute zero. And we can apply this first equation to calculate the speed of light there. And we figure out that the speed of light is decreased by 39%. I take another example here, the BEC condensate. This is a state of matter which can be formed at a very, very low temperature, a few tenths of degrees above absolute zero. And here, the speed of light, when the light is shining through that condensate, the speed can be measured, and the light is going at a very slow speed, like 15 meters per second instead of 300,000 kilometers per second. So this is because of this first equation. The speed of light depends on the temperature of the gas. This is an important conclusion. There are consequences for that here. And conversely, for sure, the speed of light could go much faster in the universe where the temperature is higher. I think there are two main consequences for this. The light rays grazing the surface of the Earth are deflected due to gravity, since light rays carries some mass. And this had been first calculated by von Sollner in 1801. And he found that the speed of light has been deflected, and he measured that, and he got a half of deviation angle, because he did the calculation for one side of the ray, the incoming on the left and the outgoing on the right. He did the calculation for one half. Anyway, he was right. And there is another experiment which is quite illustrative of that, is the ponderable experiment in the 60s, where the gamma ray photons experience a redshift when they fall towards the gravitational field, when they fall in the gravitational field of the Earth. This is the same cause. We can draw some conclusion here again. The photon mass is invariant. This is that mass, and it won't change even if it is at rest or at the speed of light or even at super luminal speed. Here it is. So the local space temperature determines mass density and pressure, and this establishes the observed speed of light. We have to recall that this speed has been measured in our closed space, in our galactic neighborhood. It has never been measured outside this neighborhood. So, if we could measure at a distance, the speed of light should be higher. I could explain that, but it should be higher outside the galaxy. Okay, let's go to the PMT4, the fifth slide, please. We can talk about the de Broglie relation applied to a massive photon. De Broglie, we call him de Broglie, and in fact, he was a French physicist. It should be pronounced another way, but this is not important here. We can call him de Broglie. He had exactly 100 years ago a great insight. He said that there is a wavelength generated by all massive particles. And in an ideal gas, in thermal equilibrium at a specific temperature. He said that. So he was able to derive a very simple equation. Lambda, the wavelength, equals h over p. P is the momentum. And in this case, p is m0c0. So we can calculate that wavelength, and it is found that the wavelength is 1.70 millimeter. It is in the millimeter region. Also, it is called microwave, but this is a millimeter wave. We can switch to the frequency domain very simply by lambda equals C0 over F, and we get HF equal M0 C0 square. This has been derived directly from his formula, lambda equal h over p. And here we can recognize immediately that these are the two famous energy relations, H equal hf and H equals mc square. That's the Planck and Einstein energy equation. We can determine the frequency f, and this is the average frequency. All that is average, mean frequency, all that is average. And we get the frequency of 137 gigahertz. This is the mean frequency of the CMB radiation. The peak frequency has been measured by satellites to be 123 gigahertz. We see that it is very close from 170. One is the peak frequency, and the other is the mean frequency. And I put a diagram on the right here showing that there are two main frequencies, the peak and the mean, close to each other. One has been calculated to be 282 kT, and the other one is 3 kT, as we said before. This translates to 160 gigahertz and 170 gigahertz. There is a very close relation between the two frequencies. So the question is raised now, is the radiation a thermal relic that happened 800,000 years after the Big Bang during the recombination period? It is impossible. The explanation of a relic left over after the Big Bang doesn't hold at all. I take another very simple example. If you turn off the light in your room, the wave ceases immediately to exist. They don't persist until the next morning or forever. So it should be the same for the relay radiation. It cannot stay forever. You need to have an entity that generates the waves. And this entity is the photon gas. The photon gas continually generates the waves. And that's why this is the reason why we can detect them. So this is another amazing result we have here because of this strong correspondence with the photon gas derived frequency. So we have found the CMB radiation origin. No doubt, it is the gas of photons pervading all space. Okay, slide 6, please. Yeah. This theory can offer much more. And here I put a great example. We can determine with two equations the mean free path L, the dynamic viscosity mu, and the photon diameter d. In fact, we have three unknown and two equations. It is not sufficient to determine all these. The unknown diameter d can be, however, estimated with the helical model, where the spires illustrated here are the trajectory of photons. They follow the same path in a helical trajectory. Excuse me. Now you can imagine that for gamma rays, there are very high frequency waves. The wavelength is going shorter and shorter when you go with higher frequency, and they come at a time when the spires or the coils of the helical wave are so close to each other that the photons hit each other and the wave suddenly collapses and there is no more high frequency gamma rays anymore. And this should happen around 1 power 10 to the power 24 Hertz. Beyond that, the gamma ray should not exist. So we can make a guess. That would be the very maximum gamma ray frequency. And by lambda equals C over F, we can determine D. D equals lambda C over F. And D is then 3 times 10 minus 16 meter, or 0.3 femtometer. That would be the diameter of a photon. With this, we can calculate both with the two equations. We can calculate the mean free path and the dynamic viscosity. Let's do the calculation. The results are for the mean free path L to be 700, a little more than 700 light years. The Milky Way diameter is around 100,000 light years, so it is much more than the Milky Way. And that's why when you look at with telescope in the far away field, we can see galaxies. They are not blurred too much. You see? So this is the reason why, because the mean free path is very, very large. Another interesting result is that the dynamic viscosity is in fact very high, something like 0.434 Pascal second. This is expressed in Pascal seconds. So it is a high viscosity gas. It is an ideal gas with a very high viscosity, excuse me, and this high viscosity gives a strong dragging effect of the photon gas around bodies in the universe, like the Earth. That range of viscosity is like heavy oil, like for diesel engines, for example. And the other gases have also some viscosity, but it is very low compared. It is in the range of 10 minus 6 to 10 minus 5. Here we have 1/2 Pascal second. The gas is very viscous. And this is an amazing result. Since the time of this writing, I have found another equation for expressing the dynamic viscosity. It is on the right here, where the dynamic viscosity depends on the diameter of the photon, the temperature, and the mass of the photon. So now we have this additional equation, and we have three equations and 3 unknowns. So we can solve them all. And we see that we were not too far off the maximum frequency of a gamma ray is 1.24 10 to 24 hertz instead of 1. We did the guess for 1.24 10 to the 1024 hertz, and here it is 125 for more. We can determine the mean free path, which is now over than 1 million of light years. And we can determine the viscosity, which is about the same, 0.444 Pascal second. You see? So we are close. At the first trial, we were rather close. So, interpretation, the photon gas pervading all space is definitely very viscous, and this explains several experiments that has been done on Earth. And also this explains the distribution of gas in the galaxies. I don't go into the details here, but the distribution can be described, the distribution of the gas, of the photon gas in the galaxy can be described rather precisely. There is a phenomenon called aberration, and this is the deflected angle when you look at stars. This is not the right, it turns out to have a deflection of the light going towards the Earth. This can be explained with the photon gas. There are numerous experiments that can receive a rather good explanation. Okay, slide 7, please. Okay. We can talk about natural constants and ask the question if they are fundamental, if they are universal, or simply if they are constants. Apparently, they are not constant, at least for the speed of light, maybe for others. And from the CMB, we can, those two constants, h, the Planck constant, and the speed of light, originate from the CMB. They both can be calculated from it. We know that first equation we got before, h equals 3 kt over f, has been deduced from lambda equals h over mc, and we get h rather close to the experimental value, 10 to the minus 34 joule second. Same for the speed of light. We can determine the speed of light this way by combination of the previous equations, and we get also a close value of the speed of light. This has been done directly from the CMB radiation. It was said that it was impossible to measure, to calculate theoretically the constants. If it's not the case, we can calculate those two constants. So we can put forward a much better definition for the Planck constant H. The definition today is the amount of energy that a photon can carry according to the frequency of the associated wave in which it travels. This is the definition of Planck constant. And you can feel that it is not a very good definition. Now with this theory, it naturally results as a ratio between the quantum of photon energy and the mean radiation frequency of the CMB radiation spectrum, or in short, 3kT over F. This is much better because here, with that small value, it shows the scale between the microcosm and the microcosm. There is a bridge of 10 to the power 34 to minus 34 between the two. A big gap. We can know that Max Planck spent a very long time searching for the origin of the constant he had invented. Now we know why. The CMB radiation it was in the 1960s, and the epoch of Planck was in 1900. So there is 60 years before the discovery of the CMB radiation. So he could not know. We can talk about the photons themselves. They have two modes. Those which are not disturbed by light rays, so they stay quiet, and we can, inside the photon gas, they can be called dark photons. They form the photon gas pervading all space. And those participating in a light ray, that means, all EM electromagnetic waves, they can be called active photons. They all have an invariant mass of 125, 604, 10 minus 39 kilogram, either when they are at rest or moving at the speed of light, or in fact at any speed. And they make up the bulk of the universe. The origin of dark matter and another thing, the missing mass of galaxies, is simply dark and active massive photons. That's the origin of dark matter, simply photons. Does it need to search any further? I don't think so. Okay. Now I make a conclusion. I make several conclusions. Yeah. So here we have gotten a concentration of unexpected results, which can be easily extended in even more domains. An entire new chapter that will take another hour to develop is cosmology. Here, the very small has the potential to describe the very large, and for sure without the Big Bang. We can also note that this theory could have been found already in the 90s, when the CMB measurement data given by satellite were available. This is actually the scientific method that has been applied with the hypothesis of a photon mass at the start, followed by a development and ending with a confirmation by observed data. We know that the scientific method is the only one method that works in physics. So we have now, with this theory, a strong confirmation that the photon carries a mass. And this is the main point. There is not a single doubt in my mind. Physics, or at least a big part of it, is put back on the right track with this photon mass theory. And here, potential discovery can be made much more easily in diverse domains by anyone willing to follow these steps. All right, I'm finished.
Well, thank you very much, Henri, for that very clear exposition. I must confess, when you first sent me the slides as a backup, I thought they were a little prolix and it might be a bit difficult to explain all the concepts to the audience in a short period of time, in an hour or so. But actually, I must say you did a splendid job. You went through very slowly and you went through all the main points of the slide.
Yeah.
And for my part, it was very, very clear. So just maybe before handing it over to some people, just a couple of observations and maybe a question or two. I noted that the speed of light being proportional basically to the square root of the absolute temperature would imply that if you just jiggle around the mathematics a bit, that the product of the electric permittivity and magnetic permeability would be inversely proportional to the temperature. So that might be interesting. It might be interesting to sort out how epsilon naught and mu naught individually change rather than the product. Just one, yeah. You actually say that the mass is invariant. Actually, Jerry here, I think, just put something up. Let's see. So photons have mass. I've heard many times that they don't. I have trouble believing in them anyway. Well, the conventional view is that a photon traveling at the speed of light does have mass. I mean, it's calculated in a similar way to the way that Henri has shown, but they would say that it has zero rest mass. So it doesn't have mass, it has zero rest mass. That's a conventional view.
That would mean that the mass is changing
Yes, quite
from
so.
the speed of light to the rest mass and maybe diminishing gradually.
Is that something that you reject?
I do, yeah.
Okay.
Mhm.
So just before handing it over, maybe to others, just one or two other things. One is your photon gas idea is quite interesting, and I'm not sure why you don't call it the ether. I mean, it could be similar to such concepts.
Yeah, I didn't put the ether word in this because, on my opinion, ether exists, but it is another level down, further, smaller, at a smaller scale, even a smaller scale. And the ether apparently is making gravity, is the cause of gravity. And also, I have I have I haven't explained that the trajectories of photons follow a helical path. I've not explained that, but I think it could be explained by the ether. This is another level.
Yes, for Franklin, who has made a comment about that, he goes a bit further. He says you're confusing it, but okay, you take it as a level down.
Yeah, a
Um,
level down. You're right. Yeah.
Just one question I had. This von Soldner 1801 calculation, which is quite interesting.
Yeah.
That's basically the Newtonian extrapolation, I suppose,
Yeah.
assuming these mass. Now that got a particular value which was accepted, and even in 1919, when the so-called Einstein value, which was twice that, was observed by Eddington in the famous eclipse expedition. Well,
Yeah.
the Einstein one, I mean, you seem to say that Soldner only took into account the ray going one way, but you have to double it to go the other way. Well, I think my calculations would be that the Soldner value is actually correct. He has actually taken the incidence and the reflection into account. And the Einstein value is not merely twice that. It's because of the two sides. It's twice it because they said there's one side because of Newtonian deflection and another amount equal to that because of the warping of space and time. It's quite a different concept.
Yeah, absolutely. Yeah, but apparently Zollner has made the calculation for only half of the path. Say he has made the calculation for the incoming ray, but the rays don't stay here. There is the same ray outgoing, so there are two passes, and he has made. Apparently, I say I don't have the confirmation. He has made the calculation for only one side. So he got half of the deviation angle.
Okay, that's the point I'm coming to. I mean, we could look into this in more detail, but you appear to be saying that the Einstein value of, say, 1.76 arc seconds is correct, rather than the 0.88 which von Soldner calculated. Are you?
Yeah. It is
okay, because some of us, including myself,
correct.
might have a different view on that, but that won't be something to look into in more detail. Now, I must apologize to the people on social media because I was showing the slides and putting them onto the maximum size. I may have missed some specific questions. If you have any specific questions, rather than just general chat between you, you might just put them in again. Just say, "Here's a specific question for Henri." But while you're considering that, I'll have a look at the green room, and I wanted to mention something that I think Henri is familiar with. James Keane, one of our regular participants in the green room, was kind enough some weeks ago to give us a sort of a preview of your talk. Insofar as there was a commonality between some of his work, and it was quite an interesting talk. But I think you felt he had missed some of the elements. Well, perhaps he wasn't concentrating on those. So perhaps I'll take the liberty of asking Jim to come up and just have a brief chat about anything in regard to what Henri has said. Do you agree? Do you dissent? Would you supplement it?
Well, hi. Thank you, Henri, for your presentation. It was very, very interesting. I've had my say more or less in about 2 hours of presentation and discussion several weeks ago, as Ian just mentioned. So I just won't repeat that, except in today's presentation, I didn't find much response to some of the concerns that I had raised, and perhaps there just wasn't time for Henri to do that, or he plans to respond to those points at some time in the future. But for today, let me just make a few comments here. One of the concerns that I did express before was that the CMB properties are inconsistent with the ideal gas model. Those properties were not explicitly considered, but I'm not asking for a reply for that now. I also find that Corniere assumes that the proton shape is a sphere, and I'm wondering about that. First, we don't seem to recognize the dependencies among the constants. So all of these constants are not independent values. And that is, in other words, you really can't derive light speed or Planck's constant if you're using some other constant, which is a measured value, which has the status of an unexplained observation. One thing that might help Henri in the future is the idea to take into account the error in measured constant values. In other words, he's saying his computed value, say the 160, is very close to the computed value or to the observed value of 170. Well, it may be if you insert in there the errors involved in the measurement of the constants used, you would find the null hypothesis that there, in fact, that his estimate and the the measured estimate are in fact not significantly different statistically. So that could actually improve his argument, I believe. If those error values in the measured constant, and those are found at nist.com, what the error is in each of those measured values. Finally, a question, because I listed a bunch of points and I don't expect a complete, response right now. But here's some questions two questions I have. In the latter slides, I'd like to ask, what is the associated wave that he talks about? What is that? He's talking about the massive particle in a quote unquote associated wave. What is that? Also, he talks about being distributed by a light ray. So what is a light ray? Thank you. I'll stop here and allow Henri the floor. Thank you.
So you mentioned about the frequencies of the CMB. One is the peak frequency that has been measured by satellites, is 170 70 gigahertz, around that. And the other is the mean or average frequency, which is different. Frequency that has been determined theoretically. So there are two different frequencies. So there is a good match when you take a look at the curve, at the blackbody spectrum, or the photon gas spectrum of frequency. There is a perfect match at this level. You raised the question, I forgot now. Give me please the other question you have.
The associated wave and the light ray.
Oh yeah.
What are they in the context of your work, sir?
Yeah, this is a particle duality that has been discovered by Louis de Broglie. He said that there is an associated wave to each particle. So this is the duality, right?
I'm not sure if I was clear. Thank you. I was not sure if I was clear about taking into account the error in the measured constant values. In other words, rather than saying 160, one could say a 95% confidence interval, given the error in the measured values for the constants used, is such. And then for the other parameter, the 170, the error or would a 95% confidence interval would be such. In other words, a range of values. It could be the overlap in the two ranges is actually showing that your estimate is more accurate than what you might claim right now. In other words, this would improve your argument, if you will, if statistics were used. And the error values used, so that you're talking about ranges of possible values rather than just a precise stated value, and that those ranges actually overlap. And if they overlap too much, one cannot say that they're actually different statistically, which is, again, bolstering your argument, I would think.
Yeah.
Okay.
I'm not sure about that. Yeah. Yeah.
Okay, well, it's an interesting point, looking at it statistically to see any differences. But I just have a very specific question here, which you may wish to comment on quickly, Andrew Castro. I'd like the presenter. I'd ask the presenter why he doesn't add vibrational degrees of freedom to his calculations, especially since he says they are oscillating. He might exceed the number of degrees of freedom that you propose.
Yes. On my opinion, there are no additional vibrational degrees of freedom for photons. But they exist in fact with atoms and molecules, as they act like little springs. It is a springy gas. The air is a springy gas, so they have additional vibrating modes. But for the photon, it is a single particle. It is a elementary particle. And to answer the other question, the particle should be like a sphere, not a cube or another
Or an
shape.
ellipsoid or something like that.
Yeah, because otherwise it won't be an elementary particles if they were not shaped like a sphere. Sphere exists in nature, as we know.
Okay, well, that's something I think Jim has looked at himself. By the way, it's a bit late in the day, but I'll put my head on the block pour mon prononciation française. I was guessing, probably quite wrongly, that had there not been an E at the end of your name, it would be pronounced Corniere. But since there's an E in the end, I was pronounced as Corniere. Now, could you tell me if that's completely wrong or
No, you are right.
I'm
It
right?
is Corniere.
You,
It is
you
Corniere.
pronounce
Yeah.
the R when there's an E at the end.
That's typical name. Yeah. Mhm.
Okay.
Okay.
Thanks very much for that. So at least we know now.
Thank you.
Okay, now just while I'm looking at any other questions, and indeed I'm going to bring people up, is there anybody? Yes, Denny has anticipated me, so I'm going to bring Dennis Allen up now, who's one of our regular participants, and indeed was the person responsible for introducing us to Henri in the first place. So, Denny, please go ahead.
Can you hear me? Can you hear me?
Yeah. Yes, Denise. Yeah.
Didn't de Broglie, wasn't his photon a two-particle photon?
Say again, please.
De Broglie's photon,
De Broglie. Yeah.
was it not a two-particle object?
No,
Not
never
a
said that.
single particle object.
It is a single object. It is a single entity.
Because J.P. Wesley has a two-particle photon, and I thought he got it from de Broglie, but maybe not. Wesley's two-particle photon is a electron and a positron combination, also called positronium. And I thought he had gotten that from de Broglie, but apparently I'm wrong. I apologize.
No, that's interesting. By the way, Henri, are you familiar with J.P. Wesley's work?
No, I'm not.
Okay, it's quite interesting. He's
Oh.
he's deceased now, but he's written a number of books. I suppose challenging, the fundamentals of classical physics. Quite a fertile thinker. We've looked into his work a lot, particularly Denny and I have. We've thought that he's a bit like Homer. He nods. He's made a few mistakes, but most of his work is actually very, very interesting. J.P. Wesley. He retired from the United States to Germany, but he died a number of years ago.
Mm-hmm.
What's the name of his book?
Scientific physics.
Scientific physics. Yeah, scientific physics. Okay. So, anything else, Danny, for the moment?
No, that's about it.
Okay. Thanks very much.
You're welcome.
That's okay. I'm remove the wrong person. I'll add you to the stream, and I'll take Danny down and see does anybody else want to come up at the moment. No. I'm wondering. Would Eric like to say anything? So I always get you at a bad time, Eric, but you're going to be one of our next speakers, I think.
I'm very skeptical about what happened. I mean, you probably won't want me. I mean, right here, I can argue with a whole list of things. I've made notes. I mean, I've worked with microwaves. There's nothing helical about it. I've seen all kinds of books about that. Temperature.
Would you like to put, just for the sake of argument, since we don't have much time today, maybe one point?
Right. I could go through all these points. The most important point is, how do you explain the wave properties? Particles don't interfere and cancel out and diffract. People have tried for over 100 years. So as soon as you have wave properties, what conventional physics has done is assigned the wave property to a non-physical probability wave. But as soon as you do that, you have all the weirdness of quantum mechanics, like non-locality, to have the idea that one of these so-called photons will go one way or another at a beam splitter. And how does that happen? And so that's the paradox of wave-particle duality. So you seem to embrace these particles without saying, well, how can it act like a wave? That's the most important problem. But the answer is it's not a particle.
Franklin, by the way, Franklin has put this very succinctly by saying, question for Henri, is light a wave or a particle?
Yeah, that's right. All right, I'll just leave it there. I don't expect a decent answer, but I'll instead of just going down my whole list, I'll leave it at that one question.
Yeah,
Okay.
thanks,
Eric. Henri?
Yeah, it's not easy to answer clearly. This is the particle and a associated wave, as de Broglie said. There is a wave associated with the particle. This is all what we can say, not in details. Always an associated wave.
But is that, forgive me, any different from anything else in the universe? I mean, de Broglie presumably would talk about matter waves, that all particles would have wave-like properties, and therefore light is no different. It's just one aspect.
No. It's a wave and it's a particle at the same time. That's the duality. Okay. That's an old debate.
well, perhaps that's a bit of an improvement on sort of conventional views, which say that it's either one or the other. Like on Mondays, Wednesdays, and Fridays, it's a wave, and on Tuesdays and Thursdays, it's a particle. You know, that's a bit of a cop out. But okay, is that all right for the moment, Eric?
He is asking. Yeah, he's asking if the kinetic energy is really the only energy. When you describe with the kinetic theory,
right,
of gas, we are talking about the kinetic energy only, but that doesn't mean that the photon can have another energy. So this is the of photon energy which has been expressed here.
What do you mean, potential energy as well?
This is a much higher energy.
As well as kinetic energy.
Yeah.
Because in an electromagnetic wave, you would have a sort of a total rate of energy change, which would be composed of two elements. One would be the divergence of the Poynting vector, I suppose, and then the other one would be the rate of change of the energy density inherent in the wave. So what's a kinetic energy? What's he saying here? Kinetic energy is not the same as internal energy, right? Well, yes. Isn't that so?
No, it is the internal energy of the particle photon. That's the kinetic energy.
Oh, you're saying it is the same. You're defining. Okay. Here's another question, by the way, I saw earlier. Can you explain the faster than light phase velocity of the particle wave duality? I think he's talking about group velocity and phase velocity, and one of them can be greater than c, and the other is.
Yeah, I don't believe at all in these two concepts, phase velocity and group velocity. I think it is not necessary to put that in view when we are talking about photon particles.
Okay.
Mm-hmm.
Because for things like dispersion, it's conventionally held to be a useful concept when you're talking about dispersion of light.
Mm-hmm.
Okay.
We can recall the Maxwell velocities of particles, and we have a curve there which shows that the particle can go much faster or much slower than the speed of light. This is actually, the speed of light is actually an average of speeds shown by the Maxwell speed distribution.
Well, that was quite an interesting concept, I think, that you brought out. This exceptionally variable speed, which in certain conditions might be 39% less or something, but in other conditions could be, walking pace could be very, very small, owing to temperature approaching absolute zero.
Yeah, the photon can even be almost stopped. So that means that the speed of light is not constant for sure. It depends. We have to put that in mind, that it depends on the temperature. And the BEC is a good example for that.
Have you any a response maybe to my comment earlier that say the product of the electric permittivity and the magnetic permeability is proportional to is inversely proportional to the temperature? Well, do you think that they both change in a similar way, or would one of them be more responsible for the variation, if you understand what I'm saying?
We need more studies for that to get a clear answer for that. For the time now, I cannot answer that precisely.
Okay, well, that's fair enough. I think you've certainly given an introduction to a field of study which I think would be very fertile to look into further. It's giving some initial promising results, but it's opened up more questions, which is great. I mean, that's what science is about. Science doesn't put an end to something, and that's what we're about in the CNPS. And you're obviously an original thinker as well. We can see that by your papers and the way you speak. So when you introduce some concept which seems to have some positive results, it doesn't put a stop to the subject. It actually opens more questions, and that's fine. That's what we're all about. Okay, I see Harry has come in. Harry, I might bring you up. I think I'm not quite sure what you want to say, but you're very welcome. Another one of our participants. So I've added Harry Ricker, and I'd like maybe Harry's response to the usefulness of your concepts or otherwise.
I'm stream is overloading my computer, so I'm going to turn off if that helps.
Yeah, okay. Because the sound was just interrupted there a little.
I'm getting a connection here.
Are you going to switch off your video and yet speak?
So it's not working.
I think we could hear your audio.
It's not working here.
Can you hear me? Yes.
I hate to mess this up. It's not working.
Sorry, what's not working? Your system. You've been having some problems, connection problems, I know. And you broke up a bit actually a moment ago, so I'm a little concerned. So if you're not able, if you wanted to put something in the comment, you could do that. Sorry about that, because Harry is one of our valuable independent thinkers and regular participants who's
Can
actually
you hear me now, Ian?
Oh, you're coming back. I can hear you, Harry. You may have to speak fairly slow because I think I speak too quickly. When one speaks a bit quickly, it sometimes becomes a bit garbled. But we could hear you there, Harry.
Okay, I'm going to make my. Could you give us a summary, Henry? Could you give us a summary of the main points of your talk? I'm not really sure I understand. What are the main takeaways that I should have as a result of this talk? What are the things?
I did a summary about this photon mass theory, but it hasn't been shown here. I said that the photon mass directly calculated from the kinetic theory of gas leads straight with the de Broglie to the CMB, to the frequency of the CMB radiation. This radiation, along with the missing mass and dark matter, the missing mass in galaxy and dark matter have a common origin. A gas forgot now. A unique gas, a unique viscous gas that originates from, I am confused now. I cannot remember, but this is the origin of dark matter. The unique gas is composed of dark, on my opinion, dark and active massive photons.
Well, certainly this viscosity, high viscosity, and the sort of postulation that it may be replacing dark matter. Those were two interesting concepts, I thought. I'm not saying I totally agree with them, but you know, they're interesting. I think.
Yeah, viscosity is an interesting concept. When we calculate it, we have a very high viscosity gas. Even if it is an ideal gas, it can have viscosity.
Because you mentioned in passing that it would explain some other experiments that I think you didn't go into, but I think what you meant, and you have it perhaps in your paper, is things like the original Michelson-Morley experiment, and then the the Miller experiment, and dragging and all this sort of thing, and the viscosity could be something that you would attribute to that.
That explains the dragging effect. If we have a high viscosity, it's like a rotating ball plunged into a basket of oil, if you want, for analogy. Yeah. So you have a dragging effect of the molecule of oil around the rotating body. And I think this is the same phenomenon that happened on the Earth. You have dragged photon close to the surface of the Earth, and less dragged photons in altitude, which has been shown by the Miller experiment on the Mount Wilson. and less when you go further in altitude.
Right, because one of our participants here, I don't think he's here today, but has postulated that one could perform a sort of an experiment of that nature in outer space to get rid of perhaps any dragging effect.
Mhm.
I think this had been actually Jim did that, but I think there was an earlier gentleman by the name of Dr. Zapfi who had proposed this to NASA, but they weren't interested in even responding to his letters, I understand.
Yeah, so that could be a good idea to make a very actually a very simple experiment to put something that measure can measure the speed of light outside the Earth in the solar system, and I'm pretty sure could get another value.
But you distinguish this from the ether, which is at a lower level. I think you might have used those words.
Yeah,
But do
yeah.
you conceive of the universe at large containing this photon gas in it, or would it not be all pervasive?
Yeah, the gas is pervading. It is everywhere. It is even above your desk. It is
Yeah,
everywhere. Yeah.
yeah. It's very similar to what I might call, this medium, which you're saying is at a lower level, but these are really maybe questions of distinction. Harry's put something in. He's probably talked about how is this area different from the 0-point energy of the quantum foam? How is this idea, I beg your pardon, different from the 0-point energy of the quantum foam? Do you think it's similar to that, or is it different?
No, it is different. I think that 0-point energy doesn't exist at all. Energy is coming from an entity, from for example the photon gas. So 0-point energy is zero. There is no no point on that.
So you see quite a distinction there, which is fair enough. The questions are coming in, but okay. Well, we have maybe a minute or two for anything urgent. If anybody in the green room wants to come back, wave your hand. And if anybody has a specific question before we wrap up, just put query. Does Henri think X, Y, Z? Otherwise, I think in the absence of that, okay. I think it devolves upon me to summarize and close the session for today. Well, we've actually done this recently on two occasions. We've had people, our eagle eyes, like people like Dennis Allen, looking out for papers which might be of interest to us and referring them to us and contacting people. Now, actually, he's done that for some other people, but they're not available at present, or they're not willing to give us talks at present. But Henri is one of the two gentlemen, the other being Peter Jackson, who's about to speak to us shortly. But Henri is one of the gentlemen who very kindly agreed to give us a presentation, and just we had some questions and back and forth discussion as to how the best format might be, and but I'm certainly very, very grateful for the talk, because I have his paper actually here. I have it on my desktop in case we needed to refer to it, and I found it quite interesting to read. But I'm much clearer now on his ideas than I was at the talk. So I think it's been a very, very useful talk today, and I'd be surprised if others didn't find it as illuminating as I did. So I'd like to thank all of you for your participation. Thank Henri very much for agreeing to get up so early, on the west coast of Canada. And he sort of made some slight apology for not being a native English speaker or something. I think that was quite unnecessary. His English was totally competent and better than my French. I can assure you of that. So we had no problems that way. And the slides, again, as I said, were actually quite illuminating. I tend to just put a few headings on and maybe talk to it, but he actually had a lot in the slides, and then he went through each area. And I don't know if you noticed, actually, and I took the liberty, it wasn't something I agreed with Henri beforehand. I used my cursor to follow the points as he was going through, and I hope that was helpful. So we have these technical sessions every fortnight, and in between, there are more normal sessions, I call them normal sessions, of the CNPS, where we do engage in fundamental discussions with regard to basic problems in physics. Now, there wasn't a talk last week. I think David Hilser wasn't available, but presumably there will be one next week, and we'll just look out for the announcements. We always have announcements when there's something upcoming, and I'll be arranging something for 2 weeks' time. 2 weeks' time. Just something about solipsism, just before we close it. We could also get outlandishly philosophical and state the theory of solipsism, where I'm the only consciousness that truly exists and everything I see is an illusion. Well, this is a bit philosophical, so. Thank you all very much for participating as usual. Thank you for the people who've come in on YouTube and Facebook, for all your comments. And I hope you found it useful discussing all these questions among yourselves or between yourselves. I haven't always been able to put up all your comments, but there are so many of them. It's actually quite positive that you're finding these things a useful forum for discussing these issues between you. And thank you, all the participants in the green room for coming up and for making all those interesting points. And finally, just once again, before the hour strikes, I thank Henri Corniere very, very much for having taken the trouble of speaking to us today. I hope we'll keep in contact. Please feel free to engage in any of our Saturday afternoon, I call them afternoon, I'm in Europe, the Saturday talks. And please feel free to keep in contact with any of us. Certainly with me, you have my email. I'd like to, continue discussions in any of these matters. And if you need any help from us or any second opinion or third opinion, please feel free to come back to us without hesitation.
Thank you, Ian, for bringing me the audience.
Sorry, say that again, Henri?
Yeah, thank you, Ian, for the audience.
Oh, for the audience. It's quite so.
You wrote to me. Yeah.
Right. Yeah. Yes. Okay.
Thank you.
Well, you're very welcome. It's our pleasure to listen to you. Bonjour, and have a good day. It's getting late here. Not quite as late because we haven't yet moved to daylight savings time. We'll be doing that on the 26th of March, I understand. So I wish you all a very good day, and I'll end the broadcast now. Goodbye.
Thank you.